Okay, so let's talk about comparing two means. Okay, so comparative studies are more convincing than simple single sample investigations. So when we do a single sample investigation, that's like chapter 23, where we test one sample t-tests. So one sample inference is not as common as comparative two sample. Okay. In a comparative study, we may want to compare two treatments, or we may want to compare two populations. In either case, the samples must be chosen randomly and independently in order to perform statistical inference. Okay? So obviously a random sample is representative, and independent samples are samples that do not influence each other. Our null hypothesis is going to be that mu1 equals mu2. Okay? So the assumption is that they are equal. Now another way of writing this, which I don't generally do, but you can do it this way. Mu1 minus mu2 is 0. It's the same thing. It's just saying if you subtract the two, they equal 0, or they're equal. A two-sided one would be that mu1 does not equal mu2. Or we could write a one-sided one, a one-tail test. Mu1 is greater than mu2, or mu1 is less than mu2. Now another way of writing these two is you would do mu1 minus mu2 is greater than 0, or mu1 minus mu2 is less than 0. Either one of those. Again, I use these right here when I do mine. Okay. So before we begin, we must check our assumptions and conditions. For comparing two means, both samples must be random or representative, and must be chosen independently. Okay, this independently. This independence assumption actually has two parts to it, which we've kind of separated. One is the 10% condition because we're choosing without replacement, and the other one is, of course, that the samples are independent. Not that each thing within the sample is independent. Okay. Also, both populations must be approximately normal. Okay. Or nearly normal. And or the other way you could write that is roughly unimodal and symmetric. And again, you would follow your rules. You know, if it's 15 or less, you'd be a little bit more stringent. If it's between 15 and 40, you'd be fairly liberal. And then, because of the central limit theorem, if the sample is above 40, then you know, due to the central limit theorem, that any sample distribution is going to come out to be fairly unimodal and symmetric. So if n size is above 40, you're good to go according to the central limit theorem. So again, we would check our data for skewness or outliers. Either way, depending on the size of the sample. If these assumptions hold, then the difference in sample means is an unbiased estimator of the difference in population. So x bar 1 minus x bar 2 is equal to mu1 minus mu2. Okay, so again, we're taking from a population. There's a population. And, we're doing mu, and then we're getting a sample x bar 1. And then from another population, we're getting another sample, u2. And this is x bar 2. And we're saying, okay, well, if we subtract, what do we estimate the difference in these two populations to be? That's basically what we're doing. And how do we estimate that? We estimate that by subtracting the results of our two samples. So what we're hypothesizing is there's no difference between these two populations. That's basically what we're saying. We're saying mu1 equals mu2. So for instance, the mean SAT math score for males is the same as the mean SAT math scores for females. Okay? And then, so what would this be? Well, this would be the average SAT score for males from our sample, and this would be the average SAT score from females from our sample. Okay? So we're basically testing to see if there's a difference. Okay, two different populations of which we hypothesize that there is no difference. All right, now the variance of x bar 1 minus x bar 2 is the sum of the variances of x bar 1 and x bar 2, which is sigma 1 squared over n1 plus sigma 2 squared over n2. Well, where'd you get that from? Okay, let me explain. Here's what we discovered last chapter. We said, okay, the standard deviation of x bar, okay, depends on the sample size, right? It is whatever the sigma is divided by the square root of n. We'll call this x bar 1. So we'll call that sigma 1. And what would be true of x bar 2? Well, it would be the same thing. So we would do sigma 2. So what we're saying here is that these two populations probably have different variation. In other words, the variation in the SAT scores of males is probably not the same as the variation in SAT scores of females. And it would not be justified to think that they are. Okay? So what we have here, we just talked about, is we have independent samples. So what we want is what we said we're doing in this whole hypothesis is we're subtracting x bar 1 minus x bar 2. So if we subtract two independent means from each other, then how do we get this? And we want the difference in the two. We basically want the standard deviation of the differences in the means. Well, do we just subtract the standard deviations? Well, the answer is no, because in chapter 17, if you remember back, we learned a very important concept. When we're dealing with independent events, we add the variances. We always add the variances for independent events. Well, we have independent events here. So what do we got to do? We got to add the variances. Well, here's your standard deviation. So then what's the variance of x bar 1? Well, we know back from chapter 6, that the standard deviation equals the square root of the variance. So hence, what does the variance equal? Okay. The variance then must equal the standard deviation squared. So to go from the standard deviation to the variance, we got to square it. So we square this side. What do we get? We get sigma 1 squared. And what's the square root of n squared? Over n. And then what's the variance of this guy? It's sigma, sorry, that's not that. It's variance. Variance of x bar 2 equals sigma 2 squared. This should be n2 over n2. So hence when we add these, we got to add the variance of x bar 1, which is sigma 1 squared over n1, plus the variance of x bar 2, which is going to be the sigma 2 squared over n2. Now, what I just got, I didn't get the standard deviation, I got the variance. I just got the variance of the difference in the means. So how would I get the standard deviation? I simply take the square root of variance, so it equals this guy right here. Okay, so the whole thing is we got to add the variances. Okay, we got to add the variance. That's the principle here. And you know that your standard deviation from the last chapter when we're dealing with sample distributions for means is sigma over the square root of n, which is going to convert to s over the square root of n because we never know sigma, right? Because that's why we're doing inference. Okay, so we're going to get a sample standard deviation. So what is it going to become is, in order to get the variance, we got to square this. Hence, that's what this is. This is this squared. And then when we get the variances, even though we're subtracting, we still add the variances, which is what we did right here. So that's the sum of the variances. So that gives us the variance of the difference in the two means. And then to get the standard deviation, you simply take the square root of that sum, and that gives you the standard deviation of the differences in the means. Okay? Okay, so furthermore, if both populations are normally distributed, then x bar 1 minus x bar 2 is normally distributed. Let me illustrate for you. Okay, I put in my list. I put in my list 3 separate data lists. Okay, let's turn the calculator on. Okay, and basically what I did here is I did L1, L2, and L3. Okay, and in this case, L1 is a normally distributed list, and L2 is a normally distributed list, and L3 is the sum of those two lists. Okay, so here's what's going to happen. Let's look at real quick. Let's see. We want to look at list 1. Alright, so list 1 is normally distributed. Okay? And then we're going to look at list 2. List 2 is normally distributed. So what I did is I did the sum, because if I do the difference, it comes out to be exactly the same. So I did the sum instead. It's the same concept. Okay? Now list 3 is the sum of list 1 and list 2. And list 1 was normally distributed, list 2 was normally distributed, so the sum of list 1 and list 2 is going to be normally distributed. So if the sum is normally distributed, then the difference will also be normally distributed as well. Okay, that's all that that's saying. Okay, so in order to standardize x bar minus 1 minus x bar 2. What does standardize do? Well, it means we're getting a z-score. So we subtract the mean and divide by the standard deviation. So what we're testing now is the differences. So it's really statistic minus parameter, right? Because this is how we normally do a z-score. We do stat minus the parameter divided by the standard deviation. Well, now we're just testing the differences. So we're going to do x bar 1 minus x bar 2 as our statistic, minus the difference in our parameter, which we hypothesized to be 0, over the standard deviation. Well, the standard deviation is that whole thing we just derived, which is sigma 1 squared over n1 plus sigma 2 squared over n2, which is the sum of the variances. So that gives us the variance. Take the square root, we get the standard deviation. However, what don't we generally know? Well, we generally don't know sigma 1 and sigma 2. So we'll substitute S1 and S2. When we do that, okay, we then convert from a Z statistic to a T statistic. So now we're going into a T test. So it just becomes x bar 1 minus x bar 2. The difference is minus mu1 minus mu2 over that whole thing. Now, the only difference is we're going to use S1 squared over N1, S2 squared over N2, which is the sum of the variances. Take the square root of it. Okay? Now this whole thing, these are the two things on your calculator. This is a two-sample t-test. And I'll go into how to use those. And this is a two-sample confidence interval. Okay? Now, in a confidence interval, what's the form of a confidence interval? Well, it's generally statistic plus or minus margin of error. Well, what are we testing in our statistic now? We're testing the difference in the two populations. So we don't have the two populations, so we use the two samples. So we're going to do x bar 1 minus x bar 2 plus or minus our margin of error. Well, how do we get our margin of error? Well, we do t with some degrees of freedom, whatever that is. And then we have to do standard error. Well, how do we do standard error? Standard error is right here. Again, we got to add the variances. So it's that same concept of S1 squared over N1 over S2 squared over N2. So that now becomes our margin of error, and this is the difference in the statistics. So what are we trying to capture here in this confidence interval? What we're trying to capture is the average difference in the means. That's what we're trying to capture. What is the average difference in the means? Is there evidence that that there's a difference in the mean SAT math score of males and females? If 0 is in that interval, then there is no evidence. If that entire interval is either above or below 0, then you have evidence that there is a difference, and we'll go into that as we move on in the chapter. All right, let's look at an example here. So resting pulse rates for a random sample of 26 smokers had a mean of 80 beats per minute, standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the mean and standard deviation were 74 and 6 beats per minute. Both sets of data were roughly symmetric and had no outliers. So is there a difference in mean pulse rate between smokers and non-smokers? And let's test at the alpha equals 0.05 level. Okay. That's what will probably be on the AP test. Okay, so first of all, let's just take this back. How do we know what kind of data we're dealing with here? Okay, that's the first thing. Are we dealing with categorical data or quantitative? Okay, now, whenever you're given a standard deviation, that's a dead giveaway that you are dealing with quantitative data. Okay, so we're definitely dealing with quantitative. They gave us means and standard deviations. That's generally not going to be categorical. Okay, so now the next question is: Are these two groups of people that we're looking at independent or not? And we're looking at smokers and non-smokers. So, smokers fit into one category and non-smokers fit into another. So they are not, when we're talking about this characteristic in their life, these are independent samples. Okay. Okay, so we're going to do a t-test, obviously, and since we're dealing with independent samples, we're going to do a two-sample t-test. Okay. So now we have two different parameters. So we're going to have smokers and non-smokers. So mu of S is the mean resting pulse rate of smokers, and mu sub n is going to be the mean resting pulse rate of non-smokers. So there's our parameter. Our assumptions and conditions. Let's see. Okay, both samples are random. The samples are independent. Okay. And let's see, for smokers you had 26, and for non-smokers you had 32. So 26 smokers and 32 non-smokers are less than 10% all smokers and non-smokers. And the nice thing here is they didn't give us the data, but they gave us this statement right here. So they told us that both sets of data were roughly symmetric with no outliers. So I don't even have to check the histograms. Now you might be asking and saying, well, if I'm taking this on a test, so I have to write that down. It's given. Yes, you do. You have, unless they tell you very explicitly, and sometimes they do. They say assume all conditions are met. If they say that, then you're good. You don't have to check assumptions and conditions. If they don't say that, even though they tell you that in the problem, you got to put it down. Okay. Name the test. This is a two-sample t-test. Test statistics and parameters. Well, let's see. Let's deal with smokers. So the number of smokers is 26. The X bar for smokers is 80, and the standard deviation for smokers is 5. For non-smokers, N sub n is 32. X bar for N is 74. And the standard deviation for non-smokers is 6. Okay. Now, we're dealing with a t-test, so we need degrees of freedom. So, when we did a one-sample t-test, you might be saying, well, we just subtracted 1, so we do a two-sample t-test, we're just going to subtract 2. Well, it's not quite that easy. It's actually a fairly complex calculation, and this is on the bottom of your page 549 in your textbook. And for a two-sample t-test, this is the calculation to figure out what degrees of freedom is. Now, we're not going to do all that. I'm just showing you it's not quite as simple as subtracting 2. Now, subtracting 2 is a good estimate, but it's actually, you got to remember, it's a fairly complex calculation. So what we're going to do is we're just going to leave that open for now, because the calculator is going to do that for us. So we're not going to do that. So now we need to obtain P. So we need a t-value, and we don't know how many degrees of freedom, but we do know we have to subtract, oh shoot, forgot to write my hypotheses, didn't I? Okay. let's go back up here. Our hypothesis, the null hypothesis, is that the mean pulse rate for smokers equals the mean for non. Now they said here, the question is there evidence of a difference? So a difference can be either way. So that makes life easy. The alternative hypothesis is that mu sub s does not equal mu sub n. Okay, so they didn't ask us, is there evidence that the resting pulse rates of smokers is lower than the resting pulse rate of non-smokers. So they just want to see if there's a difference, so that's kind of nice. So we're going to just do x bar for smokers is 80 minus the x bar for non-smokers is 74 minus the hypothesized difference. Well, if I do mu sub s, if mu sub s equals mu sub n, then mu sub s minus mu sub n is 0. So that's easy. And then we got to do our deal on the bottom, which is s sub 1 squared over n1, which is 26, plus s sub 2 squared, which is 6, over n2, which is 32. We'll put that under the square root. By the way, this whole deal on the bottom is found on your AP formula sheet, so you don't really have to memorize that. You just have to know how to just know how to plug in the players. Okay. So I can't even calculate this right now because I don't have the degrees of freedom. So I am just going to go to the calculator, and we're going to go to 2SAMP t-test, and now we got to use statistics. Okay. And it's going to ask us all these things, so we kind of need this information right here. So we're going to do smokers as our x1. So their mean is 80, their standard deviation is 5, their number is 26. The x bar for non-smokers is 74, for standard deviation is 6, and the number is 32. Okay, and we're going to do the not equal to. Okay, and do we pool? No. And the reason we don't pool, the reason we would pool, is because we assume that the variation is the same. And when we're doing categorical data, it makes sense because the calculation to get the standard deviation for p depends upon what p is and the sample size. So if you have a standard deviation for, let's say, every p-value of 0.5 that has a sample size of 100, will have the exact same standard deviation because you would simply do the square root of 0.5 times 0.5 over 100. But when we're dealing with quantitative data, in this case, we're dealing with the difference in variation of pulse rates of smokers and non-smokers. It would not be a valid assumption to assume that those two variations are equal. So when we're doing t-tests, we're not going to pool. Okay? And I'm going to go to calculate first. And the reason I did is if you look on the fourth row down, look at what popped up. DF. Wonderful. 55.95. Okay? So let's see. You say, okay, well, if I added my two n values, you would have gotten 58. If you did 58 minus 2, you got about 56. So it kind of worked out. So our degrees of freedom here, I'm going to put the exact decimal. Doesn't always work out like that. Sometimes it comes out to roughly n1 plus n2 minus 2, but then you'll do some where it's like, you know, it's like, well, where did that calculation come from? Why is the difference 6? And it's because of that formula I showed you. So it seems like with larger samples, the estimator seems to work better. With smaller samples, the estimator doesn't work as well. And then also in this case, the standard deviations are fairly close and the means are fairly close. So, all right, but enough on that. So that's how you calculate degrees of freedom. Just let the calculator do it. Makes it easy. Now, I have all the information I need here. However, I'm just going to go back and just say, okay, I have everything in, draw that up for me. Now, one thing you want to be careful of here is it's going to give you a t value, right? It's going to say the t is positive 4.153. However, you have to keep in mind here that when you do an alternative hypothesis of not equal to, you're doing a two-tailed test. So when you put this down, you put one of these down like this, and you just say, oh, it's just t equals 4.1537, and I'm just going to shade over there. It's wrong. That's not right. Okay, because there's also another tail over here, and this is t equals negative 4.1537. Okay, so you got to shade both tails. Okay, and the area that's shaded between the two of those that's 1 e to the negative fourth, so that's 0.0001. Okay, so we're going to make a decision, and we reject h sub o at the 0.05 level, and state the conclusion there is strong evidence that there is a difference in the resting in the mean or average resting pulse rates of smokers and non-smokers. Now I'm going to go and I'm just going to look here, and I see, oh, the average for smokers is higher than the average for non-smokers. So I'm going to just write a statement like, it appears that the average resting pulse rates of smokers is higher than the average resting pulse rate of non-smokers. Okay. So now we got to construct a 95% confidence interval. So our confidence interval is the difference in the two statistics. Yeah. Plus or minus t with, we'll just call it 56 degrees of freedom over the square root of S1, which would be S of n squared over n1 plus S of s squared over, this would be, and this is n sub n, this is n sub s. Okay, so our difference in these would be 80 minus 74. I got to figure out what that t statistic is. I'm going to estimate it. Let's see, let's see, actually I'm going to just reverse these because I put smokers first. It doesn't matter because I'm adding. As long as they're under there, when you're adding order, it doesn't matter. But I'm just going to put smokers first because they're first in my stuff up here. So I'm just going to do 5 squared over 26. Now 5 has to be over to 26 because that's what I'm dealing with. Smokers plus non-smokers is 6 squared over 32. So again, if I'm dealing with a 95% confidence interval, just bear in mind, just draw a little picture. I always like to do that. 95%. And what percentile do I begin and end at? Well, if I'm looking at the middle 95%, then that means I have 5% outside. That means there's 2.5% in each tail. So that means this begins at the 2.5 percentile and ends at the 97.5th percentile. Okay, I can't tell you how many times I get this one. People say, oh, it's a 95% confidence interval. We go to inverse t. And let me just put in 0.95 with 56 degrees of freedom, and oh, the t-value is 1.673, and that's totally wrong, because that's not where the percentile begins or ends. So when you do this, make sure that you draw yourself a little picture, and this should be either 0.025 or the 97.5th percentile. And again, I'm just estimating what t is approximately if I was doing this problem. It comes out to a t-value of around 2. So that's what I'm going to put down. And I'm not going to wind up doing all this math out, because the calculator can do that for us. So I'm going to just go to stat test, and we're going to find 2 sample int. There it is right there. Okay. Now, the nice thing is when we put statistics in for 2 sample t-tests, it fills them in for the other. So what we do have to keep in mind is what's first here. So what does X bar 1 stand for? That stands for the resting pulse rate of smokers. So I'm subtracting smokers minus non-smokers. I have to keep that in mind. Okay, and we're going to change our confidence level to 0.95. We're not going to pool, and we're going to calculate. And it comes out to around 3.1 to 8.9. Okay, now what is that 3.1 to 8.9 represent? Well, that is our estimate of what the difference is of mu sub s minus mu sub n. So we're saying that in effect we think that the average resting pulse rate of all smokers, because that's why we do a confidence interval, we're trying to infer something about the population, is between 3.1 and 8.9 beats per minute, higher than the average resting pulse rate of non-smokers. That's what that means right there. So again, you got to keep in mind when you're doing a 2 sample deal, you're looking at the difference. So we are 95% confident that the average resting pulse rate of smokers, because that's who was in S1, is between 3.1 and 8.9 beats per minute, higher than the average resting pulse rate of non-smokers. Okay? So that's basically what we're saying, and that's basically going to follow what we wound up getting as our result of our hypothesis test. We said, yeah, there's very strong evidence that the average resting pulse rate of smokers is different. That's what we tested for. We tested for a difference. We didn't test to see if one was higher or the other, but we also look at our statistics and we say, oh, okay, well, smokers tend to have an average resting pulse rate that's higher than non-smokers. So we know there's a difference, and this is basically what we've captured based on our statistics of what that difference is. Okay. All right. So type 1 error, type 2 error, and power. Okay. So let's go to our hypotheses. So if this is true, if the null hypothesis is true, then there is no difference in the resting pulse rate of smokers and non-smokers. Okay, so that would be a type 1 error type situation. So the reality is there is no difference. The null hypothesis is true. So what would a type 1 error be? It would be there is no difference in the resting pulse rates of smokers and non-smokers. But the test determines that there is one. Okay? So our hypothesis test failed. Okay, what we should have done is we should have failed to reject the null. But what happened is we rejected the null and we determined that H of A is true. That's what type 1 error would be. So what would type 2 error be? Type 2 error would be the alternative is true. There is a difference, but the test fails to detect it. So that's type 2 error. So there is a difference in resting pulse rates of smokers and non-smokers, but the test determines that there is not one. Okay? And then power, of course, goes with the fact that the alternative hypothesis is true. So in this case, and this is true, okay? So in our test, we determined that there is a difference. So power is the probability that the test correctly determines that there is a difference in the average resting pulse rates of smokers and non-smokers. Okay? So again, we're dealing with two sample t-tests. We're looking at the average differences.